Fuel distribution and filling stations have always been operational and environmental risks. This is because the liquids handled at the stations are flammable, causing hazards to health and risks to the surroundings. The increase in criminal activity, along with new tightened environmental and operational safety requirements and rapidly growing networks of self-service automatic stations, have posed many challenges for the design of filling stations and the improvement of their everyday operation. New positive requirements and improvement targets often cause a negative reaction somewhere else, and these chain reactions can be difficult to piece together without combining theory and practice. Most often, the best result is obtained with a real-life practice or test situation. A well-known example is the benzene additive MTBE, which substantially reduces air pollution. In the last few years, there's been evidence of a danger to groundwater from this substance, and now a lot of attention is being paid to its negative effects. A commonly known technique during unloading at filling stations is vapor recovery, which is done to prevent air pollution, but it also involves a clear increase in the risk of explosions in cases of malfunction and negligent use. For these common reasons, we in U-Cont Limited decided in 1997 to launch the Forecourt 2005 development project. In this project, we've searched for solutions to various problems arising at filling stations. It was clear from the beginning that there are many physical phenomena and chain reactions that cannot be examined only on a theoretical basis. In order to obtain the best practical information and ensure a broad-minded view, the Emergency Services College and the Technical Research Centre of Finland were invited to participate in the project, and many forecourt equipment manufacturers have also helped us in it. We constructed a full-scale filling station to simulate the different chain reactions that can occur in the forecourt area. This was built on the premises of the Emergency Services College in Kuopio, Finland. We analysed accidents that had happened earlier. For example, this case in Varkaus, Finland, where fuel pipes had been leaking for a long time and had saturated the ground so badly that an excavator's scoop sparked off a fire. Also, an official who was taking samples with a spoon burnt his hand because the spoon caused the spark and set the ground alight. This contaminated ground was an illustration of the risk entailed in long pipelines that contain several joints. A similar situation can arise from continual overfilling during unloading or from tank leakage. If these fuel leaks have access to groundwater, it will cause other forms of massive damage. Experiences and reports of explosions and acts of vandalism also helped us in designing the test station and the safety tests. The test filling station was inaugurated in August 2000, when we arranged a safety day together with the Emergency Services College. The event was witnessed by approximately 100 guests from oil companies and fire departments around Finland. None of the tests was rehearsed beforehand, so there were a few surprises during the day. Customers at filling stations very often forget what kinds of liquids petrol and diesel are, and careless fire handling and smoking is often seen at locations where there's a risk of fuel vapours. Another operational risk comes from criminal acts, which cause not only financial losses, but also safety risks. We asked the Fire Marshal course at the Emergency Services College to choose a team to study the station and its forecourt for 10 minutes, and then choose tools from the college's garage and set about stealing petrol from the station. The old way of stealing petrol is to try to milk the dispenser, but modern dispensers have good protection against vandalism. The tank's filling pipe presumably provides the most common way of stealing petrol. In this case, the offset filling point, together with mechanical overfill preventer, blocked the suction pipe from entering the tank. smoking during this kind of process increases the excitement. Some years ago, there was a case in America where thieves tried to flame cut a hole in a tank. They did not survive to tell about their experiences. Next, the thieves tried to get into the tank's skin through the access chamber. Breaking the lock on the level measuring pipe took less time than opening it with a key. This pipe has a straight connection with the tank and makes pumping of the fuel very easy. The whole process took less than 5 minutes.
Ja nyt on semmoisia vaaratilanteita, jos joku käy näitä letkuttamasta ja jättää noin venttiilin kannet auki tai noin syöttöyhteyden kannet auki ja lyötään luukun kiinni, niin bensiinihöyry tulee jatkuvasti.
We simulated a waste bin fire with 2 models of bin. The first, a traditional model where you have to open the cover, and the second, a new type with a return spring on the cover. In the traditional model, the fire propagated rapidly, and the temperature rose to close to the sparking temperature of petrol vapor. The greatest danger in this chain reaction was from the sparks that were flying from the waste bin. The model with a return spring cover was very difficult to set on fire without preventing the cover from closing. The fire extinguisher didn't work as planned because its activation was not enough to stifle the fire. But this test did convince us that waste bins at filling stations should have return spring covers to prevent fires. Using a traditional dipstick for measuring the fuel level involves safety risks that everyone should remember. Physically, it's equivalent to opening the filling pipe cover. Normally, when a filling station has a vapor recovery system, the tank and the pipelines have a slight excess pressure. If the pressures at the upper limit of the high and low pressure vent, 0.035 bar, opening the tank connection will release hundreds of litres of a very highly compounded vapor which will become explosive on mixing with air. The real explosive petrol vapor in this test was about 1,300 litres, enough to make the surrounding area explosive within a radius of about 2 to 3 meters. 1,300 litres of explosive petrol vapor is a very large quantity, which is important to remember during the next tests. The safety day continued with a test of the ventilation of access chambers. With the customer's permission, we have built all our stations since 1998 with a chamber ventilation system.